Welcome to my channel, The Discovery Desk.
Modern low-altitude airspace has become increasingly contested, saturated by mass-produced, commercially available unmanned aerial vehicles. For decades, the standard military response to airborne threats relied on kinetic interceptors. Heavy systems, like the medium-range surface-to-air missile, provide a high-altitude envelope over advancing Army formations. But engineering, manufacturing, and deploying a single advanced surface-to-air missile requires a long logistical tail and millions of dollars per shot. Compare that high-end production with the target. An adversary can assemble and weaponize an entire fleet of off-the-shelf quadcopters or fixed-wing loitering munitions for the cost of a single civilian vehicle. This chart visualizes the core economic problem of modern air defense. On the left is the multi-million-dollar investment required for a kinetic interceptor. On the right, the low hundreds of dollars required for a commercial UAV. When an adversary sends a swarm of these low-cost drones, they aren't always trying to strike a target directly. They are often executing an exhaustion tactic, aiming to deplete a formation's defense network by forcing it to expend its limited missile reserves on cheap decoys. Defending against massed drone attacks with purely kinetic systems is mathematically and logistically unsustainable. The defensive formation will run out of missiles long before the adversary runs out of drones. To address this, military strategy is transitioning toward drone spectrum warfare, prioritizing electronic disruption over physical destruction. This transition is evident in the Indian government's recent 52,000 crore rupee defense procurement package. A central piece of that package is the acceptance of necessity approval for Aakash Tarang, a newly developed indigenous anti-UAV electronic warfare system. Instead of functioning as an isolated unit, Aakash Tarang is engineered to integrate beneath existing anti-air networks, establishing the critical first layer of defense within an active military formation. By handling the high-volume, low-tier swarm threats at the ground level, the system preserves highly capable kinetic reserves for high-value threats, like incoming cruise missiles or enemy aircraft. It accomplishes this through a soft kill mechanism. Rather than launching a projectile to destroy the physical airframe of the drone, it attacks the invisible data links connecting the machine to its base. In practice, Aakash Tarang functions as an economic weapon. It restores parity to the battlefield by ensuring the cost of neutralizing a drone is lower than the cost of the drone itself. To protect a frontline unit, the system's hardware must be able to match the pace of the mechanized columns it guards. The entire Aakash Tarang system is integrated directly onto a 6x6 high-mobility chassis, enabling rapid deployment across varied terrain. The operational kill chain begins at the top of the vehicle with the detect and identify phase. This mast-mounted surveillance antenna continuously scans the operational radius, searching for the specific radio frequency emissions of hostile drones. This establishes an active, invisible situational awareness bubble that moves with the formation. The hardware is capable of classifying multiple incoming UAVs simultaneously. By independently mapping dozens of discrete signals at once, it negates the primary tactical advantage of a massed swarm attack. This continuous mobile detection ensures that advancing Army formations maintain visibility on low-profile targets, regardless of their operational speed or the density of the terrain. Once targets are mapped, the data drops to the critical intermediary step of the kill chain, threat evaluation. Inside the main cabin, the onboard unit conducts real-time signal processing to interpret the telemetry collected by the mast. The system's algorithms categorize the exact operational profile of the incoming drones, assigning specific electronic countermeasures to each one. With the targets prioritized, the system transitions to the active engagement phase, track and jam. The engagement is executed through the communication jammer array. This animation illustrates the physics of a soft kill. The system blasts the target with high-powered RF noise, saturating the specific frequencies the drone relies on to navigate. This targeted saturation severs the control loop and data link connecting the hostile UAV to its operator. Because it utilizes a multi-band array, it can isolate and target various threat profiles simultaneously, including quadcopters and fixed-wing loitering munitions. By achieving localized spectrum dominance, Aakash Tarang blinds and deafens the enemy drone without ever firing a kinetic projectile. This leads to the final phase of the kill chain, neutralization. In this schematic, the jamming antennas generate a wide-frequency 360-degree tactical protection dome over the convoy. The consequence for any UAV crossing into this envelope is a total loss of external command and navigation inputs. Stripped of outside signals, the drone is forced to trigger its internal fail-safe programming. For many models, this means halting their current vector and simply hovering in place. Other programmed fail-safes might instruct the UAV to attempt a return to its launch point, or to simply cut power to the motors and crash. While the exact operational ranges are classified, this dome secures immediate close-in defense for critical infrastructure and border operations. Ultimately, Aakash Tarang's soft kill sequence shifts the burden of air defense from a logistics problem of missile supply to a physics problem of signal control. A mature and effective air defense network requires both electronic and kinetic systems to operate closely in tandem. Integrating Aakash Tarang into the wider military architecture is a structural necessity for maintaining operational readiness. Producing this capability domestically also supports the broader goals of self-reliant defense manufacturing, securing supply chains for future electronic warfare assets. On a tactical level, this multi-tiered integration restores the economic balance of battlefield survivability. Look at this schematic. By establishing a dense electronic warfare shield at the center of the formation, the system insulates the outer kinetic engagement rings, protecting the high-tier SAMs from exhaustion tactics. But warfare is an iterative cycle. Every defensive integration eventually forces an offensive adaptation from the adversary. The emerging threat is the fully autonomous drone, swarms designed to execute complex operations without requiring a human in the loop. These units do not rely on remote control. They use internal inertial navigation and onboard optical recognition, matching live camera feeds directly to preloaded topographical maps. This renders traditional RF jamming ineffective. The drones fly through the interference because they are simply not listening for outside signals. As adversaries move towards silent autonomous swarms, ground-based architectures face a new threshold. How do you evolve an electronic kill chain to neutralize a machine that requires no external data to strike?